let's see if we can now move on to the half equation for the reduction of the manganese in the manganate ion. Let's see if I can get the titles done a bit better. Well, you get the idea, don't you? Doesn't really matter if my head's in the way now. Reduction. Something like that. So again, we're going to leave big gaps. The MnO4 minus with a gap about there has gone to some Mn2 plus with some more gaps. Got lots of space to work with, so I should be able to do everything I need to do to balance it. Which, if you look back at slide 22, is a little more complicated. I'm going to stop holding this up each time I need it, okay? You can have it open in front of you. But is the manganese the thing that's changed oxidation state balanced? Yes, it is. We've gone from 1 to 1. Oxygens, 4 there, 0 there. Well, how do I balance them? And this is a bit of a intellectual leap here. We cheat. That's the way I like to phrase this. We cheat because we were told in a reaction at the top. We were told that this was going on. We're going to make a sort of assumption now, or inference. We can imagine this reaction was being done in a college laboratory, a bit like when you were doing your required practical with the ions testing. Remember adding some chloride, bromide, iodide and the silver nitrate and seeing the colours change. You've got test tubes, you've got access to deionized water, and we've got access to one other thing. We're going to cheat again in a minute. So because these are all ions, they're also floating around in solutions in test tubes. So there's water present here. There's water involved here, even though it isn't written on yet. So we can cheat and just say, let's have some water. Let's have some water from a space point of view. Let's have the water here. I'm going to need some space there in a minute. H2O plus that. Okay, let's have some water there. That is going to annoy me. And the quick thinking amongst you will have noticed that we've got 4 there, 1 there, 4 that. Okay, we must have had 4 waters. So that's the water. Next step, balance for hydrogen. Are we balanced for hydrogen? Well, we're not anymore because I've just chucked a load on the right hand side. Well, what do I do now? I can cheat again. I do more cheating. If you remember when we did the silver nitrate test, we just chucked a load of acid in with this stuff. Not for this reason, but you know that we've got access to acid in the laboratory. This reaction needs some acid in order to function. And the acid, of course, the active ingredient in acid is H+. So we can put some H+ on this side. Let's have some H+. H+ plus the manganate going to the next side. And that must be 8 to balance it out. So, seems a little more complicated than the previous half equation, but we're now in a position to do stage 4. Let's look at those electrons. Well, -5 was the change in oxidation state. The manganese has had 5 electrons come towards it. It's gained 5 electrons in some way or other. Don't need to worry about the details of the bonding and stuff here. So, if it's gained them, we've gone from having some electrons in one place and an atom in the other to putting the two things together so that the product has got those two things combined. So that means the electrons go on the left hand side of this equation. Plus 5 electrons. Okay? 2 half equations. Right, now we just need to stick the two together in order to create the full equation. Now the full equation is a bit like, if you think back to the haloalkanes topic, we had some free radicals and we had some propagation steps and all this stuff going on, and we had things appearing on both sides of the equations. We stuck everything together, and in doing that we were able to see a overall reaction. This is a bit like the overall of reaction for this. So annoyingly, I haven't quite laid it out in a way that's going to make this easy, but to make my overall balanced equation, I just need to take everything that appears on the left-hand side of an arrow. I'm going to move my head. Everything that appears on the left-hand side of an arrow is going to be involved. So, I've got some Fe2 plus on the top. I've got 8 H pluses. Well, we'll see the problem we're about to have in a minute. I've got my order the wrong way around. 5 electrons. And now, again, I'll take everything from this side. Fe3 plus 5 electrons. That's an electron. I've got my order wrong, but never mind. We can still do all the steps, and we can lose some of it off the edge by accident. I'll get better at this as we go along. Okay, so no, it won't. Plus Mn2 plus. Sorry about this. Right. So with the last set, hang on. With the last set of propagation steps, we decided we could cross things off if they were appearing on both sides. Have a look for a moment. What's appearing on both sides? Well, it's those electrons. We want to be able to cancel out those electrons. I'm going to cross that off, get rid of them. Unfortunately, as it stands, I've got different numbers of electrons on the left and the right, so I can't do that. Cannot get rid of them. So there's a step that needs to happen before I do this. Okay, before I do my great big circle around all of these, I needed first to make sure that the number of electrons on both sides was the same. I've got 1 there at the moment and 5 there. So I need to change that to a 5. Can I do that? Well, no, I can't. I can't just ask this equation to give me 5 electrons for every ion 2 plus that's involved. I'm going to have to multiply the whole equation by 5. If you're mathematically minded, you could think of me as doing 5 times all of this stuff in the equation. The whole equation is happening. My 5's look rubbish. We're having all of this bit happening at the same time. 5 times all of this. So I need 5 of that. I need 5 of that. Okay? And I'd be doing this before you even try and combine this, because now I'm going to get in a mess if it weren't for the fact I'm on a whiteboard. So that means that now when I do this combiney thing, I can sort this out. I can get to 5 Fe2 pluses this time. This stuff's all unchanged. There's the 5 electrons from that. And now on this side, well, Fe3 plus is 5 of that. Electrons is 5 of that. Good, we're done. Now I cancel off. Big line through those 5 electrons. Big line through those 5 electrons. So my overall answer, let's think about what the objective here was. The overall answer is that I've got 5 electrons to rub off there, 5 electrons to rub off there. Don't forget there's that little Mn2 plus there. So I'm done. My overall reaction, let's just think about what we've actually done here. The examiner, the question, has given me this small, simple looking equation. I've balanced it with something that looks a lot more complicated. And that's how we use these to do that. I'm approaching 18 minutes, so I've gone on way too long. A couple of last minute things. Annoyingly, the exam board this isn't how the questions look. Okay, the questions, if I were doing this, I'd want that and a big empty space in which to write other things like this, so I can write my workings nice and comfortably. Annoyingly, what you'll normally meet is a set of half equations, is a 1 mark question, write the half equation for oxidation. Another 1 mark question, write the, something like that. write the reduction half equation, and another one now write the overall, and you've only got one little silly dotted line to do it. So that frustrates me, because I think it'd be better if we had a 4-mark question, balance that, go. I think actually on this case that would be easier to do. But yeah, that's that principle. The last little thing, you could stop there if you like, if you're feeling saturated, but one thing that we haven't talked about is you'll sometimes be asked to identify agents. An oxidizing agent is something we can chuck into our test tube in order to oxidize something else. And the manganate ion is a popular choice. Okay, you can see that because of this reaction, the Fe2+, the iron 2+, has been oxidized to iron 3+. You can see that because of that, that's happened. So that, can I fit this on? I remember I decided I wouldn't use different colours. That is the oxidizing agent. It's accepted some electrons from this, and that's led to that being oxidized. Okay, it's an electron acceptor, and so in the language that we've been using today, it's been reduced. The oxidizing agent has been reduced because it's accepted some electrons from something else. We can apply the same argument to identify that this could be called the reducing agent. Don't normally call it that, but you could think of that as the reducing agent because it's donated electrons to this. It's in total managed to donate 5. Once we balanced it, we've donated 5 electrons into it. So it itself has been oxidized. That's another thing from the front page. Okay, thanks for watching. You rewind and pause as you need, and hopefully if this model works, we'll do a few more of these.